Okay, so we've finished talking about snow loads, and there are other kinds of loads. There are lateral loads, and those are things like wind, earthquakes, floods, earth pressure, that type of stuff. Those are lateral loads. Now, wind loading is another design load that has an impact on the design of a structure. And wind loads can vary depending upon their location and the height of the structure. These figures are referred to in the exposure category sections of building codes. For low-rise buildings, the wind load can be transferred through shear walls, like masonry walls in an elevator shaft, and an exterior masonry wall or steel bracing in the structural frame. So wind loads come and give you lateral load on the walls. They give you downward pressure on the roof, and as the wind travels over the roof, it also creates upward pressure. It can overturn structures, and they do specify for wind loads in building codes. Another design load is earthquakes, that's EQ, and there's vertical and lateral forces involved in earthquakes. It's a very dynamic type of load. And building codes can simplify loading for people. Um, the earthquake or seismic loads are based on the location of the structure, the type of soil on the building site, the type of construction, and the building's mass. Also, the shape of the building has a lot to do in earthquake load designing. Seismic maps depict the potential risks for earthquakes in various areas, and building codes will simply include loading conditions for structures. Now, we're going to be talking about flood loads in later lessons, but for now, the the base flood elevation is given as BSE. Then we have also got to know that flood proofing is involved in keeping a habitable space dry. Design loads are soil pressure. Soil pressure loads depend on the type of soil and the depth of the soil adjacent to the structure. More granular soils will apply higher pressure. Sandy soils would be a problem. As the depth below grade increases, the soil pressure typically increases, similar to the way water pressure works. And that's what they're depicting here. Up here, there's very little force. Down here, there is a lot more force. It just increases as you go deeper into the ground. Now, as for load types, a uniformly distributed load is applied evenly over a large area, like boxes of copy paper that are stacked from wall to wall in a room. The dead load of a roof system is uniformly distributed across the entire roof framing system. Live load is often given a uniformly distributed load and is assumed to be evenly distributed across an entire area. A concentrated load is a load that's applied to a small area, like a vertical stack of 5 copy paper boxes. So in this picture, we have a small vehicle on the roof of a building. That would be considered a concentrated load. Although the load may actually be distributed over a small area, it's often assumed to be applied to a single point. Now, here we go. These are different load combinations. So a building will be subjected to many different loads simultaneously, and codes specify combinations of loads that have to be considered in design. So here's the legend over here for what all these letters mean. D, which is dead load, plus L, which is live load, plus L sub R, which is a roof live load, or S for snow, or R for rain. And then you can have any of these other two. This emblem right here means the word coefficient. So that 0.6 is a coefficient. That's what that is right there. You'll notice here that for earthquakes, you can have D plus L plus S, which is snow load, plus E divided by 1.4, and E is the earthquake load. The building dead load is the only known load. All other forces vary in magnitude, duration, and location, and the building is designed for a design load possibilities that may never happen. Now, load path. This illustration really depicts how loads travel through a building structure. All loads are traced to the foundation, so everything is always trying to go down to the foundation, so it's going out and down. So the path that a load travels through the structural system, they call that tracing or chasing the loads, and each structural element has to be designed for all the loads that pass through it. So here we have the earth pushing back up, or the ground pushing back up against the footings and also against the floor, and on this footing here, and then the weight of the building is all coming down. And you can see these arrows are larger as you go down further and further and further. Load path. In this structural steel frame, the green applied load travels through the structural system taking 4 different paths. Those are the red arrows, and simultaneously it travels to finally reach the supporting soil. So the loads here are going to the outsides and then coming to the closest column and then going down to the ground. Some load does go in the opposite direction, but not as much because this is a greater distance here to these back legs. So each of the structural systems inside of a structure has to be analyzed to determine the loading that it must carry. If the load path of an applied load passes through an element, the structural elements have to be designed for that load. And here's a list of different structural elements in a building. And then load chasing for structural design. The structural design is performed by chasing the loads of the dead and live load from slabs to beams to girders, then on to the column or walls. The loads are then carried down to the footing or foundation walls and finally to the earth below. So we're going to start looking at calculating some of these loads in our exercise 2.3.3. No, 2.